Imagine hundreds of tiny drones acting as a single mind. Now imagine that mind being attacked. Picture a flock of birds sweeping the sky. Replace birds with small drones, each with cameras, radios, and processors. They launch together, spread out, and share what they see. Commanders set objectives, but the swarm decides actions in milliseconds. Militaries prize speed, scale, and resilience. Yet the same links and code that knit this collective together also create weak points. That twist changes everything. So what exactly is a drone swarm? Think of a team sport. Each drone is a player with sensors and rules. They share feeds and adjust roles on the fly. No single leader issues every command. Instead, consensus algorithms let them agree on tasks. That makes the group resilient if individual drones fail. But it also turns the swarm into a system, not a single airplane. And systems have surfaces hackers can probe. Sensors are the swarm's eyes and ears. Optical cameras map terrain. Infrared finds heat signatures. Some swarms add miniature radar to detect moving targets. Onboard AI filters raw data and sends only useful cues to neighbors. That reduces bandwidth and speeds decisions. Each drone's view stitches into a richer picture. But fused sensor data can be confusing under attack, and that confusion becomes an entry point for adversaries. Networking is the swarm's nervous system. Drones use low-latency links to swap updates. Mesh networking lets messages hop between units if one node drops. Edge computing keeps decision loops on board, reducing dependence on long-range links. Engineers tune frequency, bandwidth, and routing to avoid single points of failure. Still, radio waves travel through contested airspace and invite jamming, interception, or replay attacks, problems that demand careful design. Decision-making happens fast. Consensus algorithms let the group pick search patterns or targets without central control. Engineers program behavior rules, avoid collisions, fan out, or form a screen. Humans set goals and constraints, then let autonomy handle split-second choices. This balance gives speed without removing oversight. But when communications degrade, those behavior rules must ensure safety, or the swarm risks making dangerous choices on its own. What happens when GPS disappears? Swarms use visual odometry, inertial sensors, and terrain mapping to navigate. They run fallback routines and pre-planned behaviors to remain useful under denial. Digital twins and massive simulations train those fallbacks in virtual battlefields. Testing in harsh conditions reveals failure modes before real flights. Still, degraded navigation raises the risk of misplacement or unintended collisions, and that risk can be exploited by clever adversaries. Why do militaries pour money into swarms? They deliver mass cheaply. Hundreds of low-cost drones can overwhelm defenses designed for single high-value targets. Losing a few units rarely stops a mission. Swarms also act fast and adaptively, creating tactical dilemmas for defenders. They can scout, jam, relay signals, or serve as expendable decoys. But value attracts attention. Every capability invites countermeasures and exploitation. History shows swarms are real, not hypothetical. In 2016, hundreds of microdrones executed coordinated behaviors in a Pentagon demo. DARPA's Offset explored urban swarm tactics. The Navy's Locust program tested mass launches from ships. Allied nations run exercises combining air and ground robots. These projects move technology from lab curiosity to doctrine. If swarms scale, they change operational math, and that scale creates new cyber pressures. Now the hard part, the attack surface. Radio jamming floods frequency bands with noise to block messages. Spoofing feeds false GPS signals to mislead navigation. Weakly secured radios invite eavesdropping or command injection. Compromised firmware or supply chain elements can hide backdoors. Adversarial inputs aim to fool AI perception. Each vector looks different, but all exploit trust in signals, code, and hardware. And trust is a fragile commodity in contested environments. Jamming is blunt but effective. Send noise on the right channel and you blind coordination. Defenders fight back with frequency hopping, directional antennas, and mesh rerouting. They also design autonomy to degrade gracefully. returning to base or holding pattern when links vanish. Those safeguards reduce mission failure, but jamming can still impose friction and buy time for adversaries to act. GNSS spoofing is more subtle. An attacker broadcasts counterfeit satellite signals and nudges drones off course. Swarms counter this with sensor fusion, visual mapping, inertial navigation, and cross-checks between drones. Authentication of PNT signals and anomaly detectors can flag impossible jumps. Yet a sophisticated spoof remains dangerous, especially in GPS-dependent mission phases. The result can be delayed effects, lost assets, or worse. Data link integrity matters. If radios use weak encryption or poor authentication, attackers might inject commands or eavesdrop on telemetry. Modern designs use mutual authentication, signed commands, and rotating keys to limit that risk. Secure hardware modules store secrets and verify updates. Command provenance must be provable. Without it, an attacker could imitate a controller, a nightmare scenario defenders obsess over. Software supply chains create hidden threats. A malicious component or update can slip into production and spread to fleets. Defenders employ code signing, hardware roots of trust, and strict update pathways. They audit vendors and lock down manufacturing. Still, globalized supply chains make assurance complex. A single tainted component can ripple through many systems, so provenance matters as much as code quality. AI models themselves can be a risk. Adversarial inputs can fool perception systems. Tampered models can behave unpredictably. Defenders use ensembles, robust training, and runtime monitors to detect drift. They also keep humans in or on the loop for critical decisions. Still, AI failure modes can be subtle, causing slow degradation rather than abrupt collapse, which makes detection harder in hectic operations. Physical capture of a downed drone poses a real threat. Opponents can extract firmware, keys, and design secrets. To limit damage, systems use secure elements and rapid key erasure on crash. Partitioned architectures hide critical subsystems from recovered units. Still, clever reverse engineering can reveal tactics and vulnerabilities. Protecting hardware on the battlefield is as important as protecting software in the lab. C. What could happen if defenders fail? Communications loss can force fallback behaviors like return to base or holding patterns. Spoofing could nudge a swarm off mission. Intercepted telemetry reveals tactics. In the worst cases, command injection might let attackers redirect assets. Designers aim for graceful degradation, simpler, safer behavior under stress. The goal is never to create chaos, but to ensure safety when plans break. Defense in depth is the practical answer. Layered encryption, authentication, intrusion detection, and health checks reduce single points of failure. Zero Trust networking treats every node as untrusted until proven safe. Secure firmware signing and hardware roots of trust protect updates. Runtime monitors watch for anomalies. These measures make exploitation costly and improve resilience in messy, contested environments. But they also add complexity and operational overhead. Resilient PNT blends GPS with inertial systems, terrain matching, and visual odometry. Cross-checks and plausibility tests flag impossible jumps. Redundancy keeps navigation reliable when satellites fail. Training models on degraded inputs sharpens perception. The aim is to avoid single-point reliance on any one signal. That redundancy costs weight and power, but it buys survivability where it matters most. Supply chain assurance and continuous testing close gaps. Teams vet suppliers, lock firmware provenance, and run red team exercises. Labs simulate jamming, spoofing, and degraded comms to measure responses. Field trials validate designs under real stress. This continuous loop of test, learn, and improve hardens systems. The process is expensive, but it prevents cheap attacks from turning into strategic failures. Beyond war, swarms serve civilian roles. They map post-storm damage, monitor crops, and inspect power lines. Those peaceful uses borrow hardened techniques from defense. Conversely, civilian incidents can teach militaries about resilience. Security practices spill over both ways. Thinking about dual use helps shape standards and safety norms before risky capabilities spread uncontrolled. Ethics and policy must follow technology. Human accountability, clear rules of engagement, and proportionality remain essential. International dialogues and humanitarian groups influence limits on autonomous use of force. Governments and industry must define roles and responsibilities before autonomy scales. Without those guardrails, the technology risks outpacing the norms that keep it safe. Looking ahead, expect mixed-domain swarms combining air, ground, and marine units. Autonomy will improve onboard perception, lowering GPS dependence. Counter-swarm systems will get better at detection and electronic protection. Standard interfaces will enable allied systems to interoperate. The big challenge remains scaling security quickly and affordably as swarms become common. That race will shape doctrine and procurement. Quick recap: swarms gain power from collective sensing and distributed decision-making. Their cyber risks include jamming, spoofing, compromised links, and supply chain threats. Defense techniques focus on layered security, resilient navigation, safe autonomy, and continuous testing. Real programs already show what works and what doesn't. The final piece: policy and ethics must keep pace with technical advances or risk outstripping control. If you follow security or defense, this is a field to watch and shape. Engineers build resilient systems, policymakers set rules, and operators run exercises to learn hard lessons. The technology offers benefit and peril. Smart design can make swarms safer and more useful in peace and war, but omitting safeguards invites failure. Which path will dominate depends on choices made now. If you found this useful, like the video and subscribe for more explainers. Tell us in the comments which swarm risk surprised you most.